Welcome to The Explainer. Today, we're diving headfirst into the incredibly versatile world of amines. We'll be breaking down exactly what these compounds are, starting from their microscopic atomic structure all the way up to their massive real-world applications. If you've ever wondered how chemists manipulate molecular structures to create the medicines and materials we rely on every single day, you are absolutely in the right place. So let's jump right in. Okay, think about adrenaline, that totally crucial blood pressure regulator. Or Novocaine, the synthetic anesthetic that's literally saved us all from a nightmare at the dentist. And then there's Benadryl, the standard antihistamine you probably have sitting in your bathroom cabinet right now. So, what could these three wildly different biological and synthetic compounds possibly have in common chemically? Well, the answer is they're all amines. Amines are essentially the highly adaptable cousins of ammonia. By taking a standard ammonia molecule and strategically replacing one, two, or even all three of its hydrogen atoms with alkyl or aryl groups, chemists unlock this entirely new class of organic compounds. And it's exactly these kinds of simple atomic-level substitutions that make all those vital medicines possible in the first place. All right, here's our game plan for today. First, meet the amines. Second, naming the derivatives. Third, synthesizing amines. Fourth, physical properties and basicity. And finally, diazonium salts and dyes. Let's kick things off with Section 1, Meet the Amines, the atomic architecture. Just like ammonia, the nitrogen atom right at the core of an amine is sp3 hybridized, which gives the whole molecule this really distinct pyramidal geometry. The nitrogen is trivalent, sure, but the true protagonist of this story? It's that unshared pair of electrons sitting right there in the fourth orbital. Because of the sheer repulsion from this lone electron pair, the bond angle, actually let's call it the CNE angle to be precise, is squeezed down to be slightly less than your standard 109.5 degrees. In trimethylamine, for instance, it's about 108 degrees. And that lone pair of electrons is going to be absolutely crucial for how these molecules behave a bit later on. Now, amines are categorized by a really simple scaling mechanism based entirely on how many hydrogen atoms we swap out. If we replace just one hydrogen atom of ammonia with an alkyl or aryl group, boom, we get a primary or 1-degree amine. Swap out two, it's a secondary amine. And if we go all the way and replace all three hydrogen atoms, we've created a tertiary amine. What's kind of fun here is that in secondary and tertiary amines, those replacement groups can either be identical, which we call simple amines, or they can be entirely different, which gives us mixed amines. Moving right along to Section 2, Naming the derivatives. Common versus IUPAC systems. It's always fascinating to contrast the older common naming conventions with the rigorous IUPAC system. In the common system, chemists usually just name the alkyl group and stick the word amine at the very end. Pretty straightforward, right? Like N-propylamine. But the IUPAC system takes it a step further. It derives the name from the parent alkane, drops the E, and adds amine. But more importantly, it leaves absolutely zero ambiguity by clearly tracking the carbon chain length in the exact position of the functional group. Notice how N-propylamine becomes propan-1-amine, while its isomer, isopropylamine, is propan-2-amine. It even handles multiple amine groups seamlessly. Hex-methyldiamine just becomes hexane-1,6-diamine. It is a total lifesaver for chemists trying to decipher exactly what they're working with. All right, Section 3, Synthesizing amines, the chemist's recipe. So how do we actually make these things? Well, our first preparation method is a classic nucleophilic substitution called aminolysis. Here, you take an alkyl or benzyl halide and introduce it to an ethanolic solution of ammonia in a sealed tube, heating it up to 373 Kelvin. The ammonia acts as a nucleophile, meaning it directly cleaves the carbon-halogen bond and replaces that halogen with an amino group. It's a really simple, straightforward way to attach that amine group. But there is a bit of a catch. The primary amine formed can sometimes just keep reacting in the same pot to form secondary and tertiary amines, so you can end up with a bit of a messy mixture. If you want a much cleaner, more controlled recipe, you turn to the Gabriel phthalimide synthesis. You start with phthalimide. Treat it with ethanolic potassium hydroxide to make a potassium salt, heat that salt up with an alkyl halide, and finally perform alkaline hydrolysis. And out pops a perfectly pure primary amine. So the absolute crucial takeaway here is its limitation. This highly specific, elegant sequence only works for preparing primary aliphatic amines. You literally cannot make aromatic primary amines this way, because the aryl halides just won't undergo that necessary nucleophilic substitution in step 2. No way around it. But chemists have another brilliant trick up their sleeve, the Hoffmann bromamide degradation. You treat an amide with bromine and a strong base, like sodium hydroxide. And what happens next is basically a molecular magic trick. The alkyl or aryl group actually migrates completely away from the carbonyl carbon and attaches directly to the nitrogen atom. The result? You get a primary amine that has exactly one carbon less than the amide you started with. This is the absolute perfect reaction, a real game changer, honestly, when a chemist is designing a synthesis route and needs to intentionally chop down a carbon chain. Which brings us to Section 4, Physical Properties and Basicity, Observing Amine Behavior. There is a super fascinating trend in how these molecules physically behave, especially regarding their boiling points. Primary amines actually have the highest boiling points of the three classes. Why is that? Well, they have two hydrogen atoms available on the nitrogen to form strong intermolecular hydrogen bonds with their neighbors. Think of them like two hands holding on to other molecules. Secondary amines only have one hydrogen, so their intermolecular association is a bit weaker, leading to a lower boiling point. And tertiary amines, they have zero hydrogen atoms attached to the nitrogen. Literally no hydrogen bonding going on at all. So they have the lowest boiling points. This same hydrogen bonding mechanic also dictates solubility. Lower aliphatic amines are readily soluble in water, but as those bulky hydrophobic alkyl chains get larger, that solubility just drops off a cliff. Okay, let's talk about basicity. Remember that lone, unshared pair of electrons on the nitrogen we talked about earlier? That's what makes amines Lewis bases. They really want to donate that electron pair. But the molecular neighborhood they live in really matters. Alkylamines are actually stronger bases than plain old ammonia. This is because alkyl groups are electron-releasing. They actively push electron density towards the nitrogen, making that lone pair even more desperate to grab a proton. On the flip side, aromatic amines, like aniline, are weaker bases than ammonia. That big, bulky benzene ring is electron withdrawing. It pulls the electron density away from the nitrogen, making that crucial lone pair way less available. But here's a wild twist for you. In an aqueous phase, it's not just about pushing electrons. Solvation effects and steric hindrance come into play. This means secondary amines often end up becoming the strongest bases in water, totally beating out primary and tertiary ones. It is a crazy, delicate balancing act of atomic forces. Finally, we reach Section 5, Diazonium salts and dyes, the macro impact. Let's take a close look at benzenia diazonium chloride. Diazonium salts are synthesized from primary aromatic amines, and they are incredibly vital. This specific one is a colorless crystalline solid that dissolves really easily in water. It's surprisingly stable when you keep it ice cold, but it is highly, highly delicate. It decomposes incredibly easily if you let it dry out. But despite this extreme fragility, it is arguably one of the most essential intermediates in all of organic chemistry. And here is exactly why they're so essential. Diazonium salts are the ultimate chemical stepping stones. They mostly undergo two types of reactions. First, the diazonium group can be entirely displaced, just kicking out nitrogen gas, which lets chemists easily substitute in halogens or create phenols. Secondly, they can undergo coupling reactions. By keeping the diazo group intact and linking up with phenols or other arylamines, they form azo compounds. And these azo compounds, they are the literal foundation of the vibrant, colorful azo dyes used globally in the textile industry. This is the chemistry coloring the clothes you're wearing right now. Which brings us to our final thought for today. Since the chief commercial use of amines is serving as these vital intermediates in the synthesis of medicines and fibers, I want to leave you with a question. Knowing how heavily we rely on things like adrenaline, anesthetics, and the dyes in our textiles, how would modern healthcare and industry look without these simple ammonia derivatives? It's kind of mind-blowing to think that just swapping out a few hydrogen atoms on an ammonia molecule has literally reshaped the fabric of the modern world. Thanks so much for joining me on this explainer, and I really hope this sparked a new appreciation for the hidden chemistry going on all around us.